All right, this is pre-AP Precalculus, section 10.2. We are verifying trig identities, which means we're making the left and right sides of the equations equal to each other. Let's check this out. Consider for a moment this equation. We got secant of theta minus cosine of theta equals sine of theta times tangent of theta. Show that both sides of this equation are equal if theta is pi over 6. So let's check this out. So we got secant of pi over 6 minus cosine of pi over 6 equals sine of pi over 6 times tangent of pi over 6. Quick reminder about pi over 6. Pi over 6 is in quadrant 1. That's the reference angle. Pi over 6 is 1/6 of pi. 1/6 of pi is 30. So we could make this, I'm doing a terrible job here. We could make this a unit circle. Doesn't have to be. That's how most of you remember this, so we'll say this is 1. Opposite pi over 6 is going to be half of that. Opposite pi over 3 is going to be square root of 3 over 2. Secant of pi over 6, that's reciprocal of cosine. Cosine would be the x value, square root of 3 over 2. So this is going to be 2 over the square root of 3. Cosine of pi over 6 is the x value. It's square root of 3 over 2. If you didn't draw a unit circle here, if the radius wasn't 1, then cosine would be x over r, and secant would be r over x. Sine is y over r, which is going to be a half, times tangent. Tangent is a little bit of a mess here. That's y over x. This all just needs simplified. On the left side, we want to get common denominators. So if I multiply the left top and bottom by 2, I'm going to get 4 square roots of 3. Then this next fraction, if I multiply the top and bottom by the square root of 3, I'm going to get common denominators. I'm just going to keep working on the left. I'll come back to the right in a minute. So once you have common denominators, you subtract the numerators. Square root of 3 times square root of 3 is 3. So this becomes 1 over 2 square roots of 3. The denominator is not rationalized, but that's okay, because maybe the right side it won't be rationalized either. This is a complex fraction, which we could rewrite as 1/2 times 2 over the square root of 3. A couple different ways that's true. One, if you take the numerator and multiply by the reciprocal of the denominator, that checks out. If you decide to multiply this by 1 in the form of 2 over the square root of 3 over 2 square roots of 3, you're going to get the same thing. If you want to get rid of your denominators and just multiply top and bottom by 2, you're going to get the same thing. Regardless, you're going to get that fraction. So then these 2's cancel. So we end up with 1 over 2 square roots of 3, which is what the left side was a little bit ago. So we have just verified that this equation is true if theta is pi over 6. But that doesn't show us that this is true for all values of theta. It just tells us it's true for this specific angle. Sometimes you'll be asked to do things like that. But in general, we're going to do this for all angles. So here is this same problem, but now we're saying theta could be any angle. It's not just pi over 6. I recommend starting with the more complicated side first. The more complicated side to me for this is the left side because there's subtraction. Why is subtraction more complicated? Because if I change the left side to in terms of sine and cosine, I end up with two things that I'm subtracting, one of those being a fraction. Subtracting fractions is a pain in the rear end because you need common denominators. So I'm going to multiply cosine over 1 by cosine over cosine to get common denominators. It's going to give me 1 over cosine of theta minus cosine squared of theta over cosine of theta. Once you have common denominators, you subtract the numerators. Denominator stays the same. And then I recognize this little fella here, just doing a little bit of side work. Sine squared of theta plus cosine squared of theta is 1. If I subtract cosine squared of theta from both sides, I get that 1 minus cosine squared of theta is the same as sine squared of theta. I'm going to sneeze. I apologize in advance. Oh, wet and wild. So now we got sine squared over cosine. Now at this point I'm stuck. I don't know what to do next. When I get to a point where I think I don't know how to simplify it more, then I start looking at what does the right side say? Well, the right side says sine times tangent. I have sine squared over cosine, and I recognize that sine squared is the same thing as sine times sine. By writing it that way, I now have a sine that I'm multiplying on the left and right. So those are the same. Now this divided by cosine, I'm going to write it underneath of this sign here. And guess what this little fella is? This is the same as tangent, which is what the right side was all along. Once the right and left sides are identical, then you have proved this is a trig identity. Number 2, I'm going to start with the left side because it's more complicated. I think starting with the more complicated side is the wise choice because it can be simplified a lot. I'm going to change this to in terms of sine and cosine. That works for a lot of problems. Cotangent is the same as cosine over sine. Oh, check this out. Sine divided by sine cancels. Now we have cosine of theta over cosine of theta. Oh, that's equal to 1. Anything divided by itself is 1. Oh, look at the right side. We are multiplying two reciprocals. So that's also equal to 1. Yay, ones. Number 3, same directions. The left side is clearly more complicated. So I am going to, you got a couple choices. I could distribute this, then change things in terms of sine and cosine, or I can change things in terms of sine and cosine and then distribute. I'm going to distribute first. So secant of theta times cosecant of theta minus, and then I'm going to have secant of theta times cotangent of theta times cosine of theta. Now, if you recognize right now, we are multiplying secant and cosine together. Those are reciprocals. So that becomes 1, and I can change cotangent to cosine over sine. Secant of theta times, I kind of wrote this poorly, my apologies. Secant of theta times cosecant of theta is going to be 1 over cosine of theta times 1 over sine of theta. I want to get common denominators, so I'm going to multiply the fraction on the right by 1 in the form of cosine over cosine. That's going to give me 1 minus cosine squared of theta over sine of theta cosine of theta. Now in the previous problem, we established that that was the same as sine squared of theta. Let me remind you why with a little bit of side work. Sine squared of theta plus cosine squared of theta is 1. If you subtract sine squared of theta from both sides, you get that 1 minus cosine squared of theta is sine squared of theta. Then we can cancel a sine from the top and bottom because we are multiplying the top and bottom by those. Gives us sine of theta over cosine of theta. And at this point, what do? We look at the right side of the equation. It's tangent. Well, so is the left because sine divided by cosine of the same angle is tangent of theta. Excellent. Finished. Number 4. Let's see. The right side of this equation, the left side's more complicated, which is usually where I start. But I recognize a Pythagorean identity here. Secant squared of theta is the same as 1 plus tangent squared of theta. The parentheses I'm using here have no mathematical value. I'm just showing you what's being substituted. Tangent squared minus tangent squared of theta, those cancel. So we have 1 plus 0, which is just 1. Interesting. That means this left side has to also be 1. So check this out. We got sine in the numerator here. We have cosecant in the denominator. If I want to make this so it's in terms of sine and cosine, I can take cosecant and reciprocate it, which makes it sine, goes to the other side of the fraction. So this is sine of theta times sine of theta. Similarly, if I want to move secant to the top, I change it to its reciprocal. So we got cosine of theta times cosine of theta. Sine times sine is sine squared. Cosine times cosine is cosine squared. Hey, I know what that is. Sine squared plus cosine squared of theta is 1. That's what the right side was all along. Number 5. I'm going to start with the left because I think the left's more complicated. I'm going to change things in terms of sine and cosine. Is that how you do every problem? No. But it could be how you do every problem, I think. I need common denominators. I'm going to multiply sine of theta over 1 by 1 in the form of sine over sine. That's going to give me 1 minus sine squared of theta over sine. Let me just show that. Once you have common denominators, you can subtract the tops, leave the bottoms the same. 1 minus sine squared of theta, well, that's cosine squared of theta. How do I know that? Let me show you with a little side work, as they say. Sine squared of an angle plus cosine squared of the same angle equals 1. If I subtract sine squared from both sides, I get that cosine squared of theta is 1 minus sine squared of theta. So that's how I know that that's cosine. Then, I don't know what to do next. That's the truth. But I look at the right side of the equation, which has a cosine times something. So I'm going to separate this cosine squared into a cosine times something, and that something is going to be cosine over sine. Notice how the things highlighted in purple are the same, which must mean the things that are not highlighted have to be the same. And if you check back in your brain or your notes, cosine of theta over sine of theta is cotangent, which is what the right side was all along. Done. Number 6. In your above work, you verified this identity was true. Explain why, if theta was pi, that would not be an appropriate value to show that these are an identity. Well, let's try it. Cosecant of theta, we're going to change to cosecant of pi minus sine of pi equals cosine of pi times cotangent of pi. Well, let's review real quick where this pi is in the coordinate plane. In the coordinate plane, pi is the negative x-axis. Here, x is negative 1, y is 0, and r is 1, assuming it's a unit circle. Cosecant, reciprocal of sine. Sine here would be would be y over r, which is 0 over 1, which is 0. Cosecant of theta then is reciprocal of that, which is 1 over 0. Minus sine of theta, as just discussed, is 0 over 1, which is 0. Cosine of theta would be x over r, which is going to be negative 1. Cotangent of theta is going to be x over y, which is negative 1 over 0. Well, 1 divided by 0 is undefined. Minus 0 equals negative 1 times 1. Negative 1 divided by 0, also undefined. If your equation has an undefined in it, you can't do anything with that equation. It just doesn't make any sense. So here's why this is a bad choice to use pi to verify that that's an identity. When theta equals pi cosecant of theta and cotangent of theta are undefined. That's a good enough explanation of saying why that's an inappropriate value to choose. Number 7. Analytically show that the equation represents a trig identity, the same directions that it were before, so let's see what we can do with this. This is the first Pythagorean identity. That's equal to 1. 1 over tangent of x is the same as cotangent of x. The right side was cotangent of x the entire time. Number 8. This whole left side somehow simplifies to tangent. So we could multiply this stuff out, then change the sign and cosine, or we can change the sign and cosine first. I'm going to do that. I'm going to change the sign and cosine first for this one. How do I decide? I just randomly decide. I don't know which one's going to be better. Now, before I multiply this stuff out, I want to make this one fraction. I want to make this one fraction. This one on the right already has common denominators, so it's going to be 1 minus cosine of theta over sine of theta. This one on the left, if I multiply the 1 times cosine of theta over cosine of theta, I'll get common denominators. And then when I add those, I'm going to get 1 plus cosine of theta over cosine of theta. Now I'm going to multiply this together. When you multiply two fractions, you multiply the tops, you multiply the bottoms. The bottom's just going to be sine times cosine. The top is going to be 1 minus cosine squared of theta. Let me provide more of an explanation for that, although you don't have to show this work. What's the relationship between 1 plus cosine and 1 minus cosine? Well, those are conjugates. When you multiply two conjugates, you get the first term squared minus the second term squared. And 1 squared, of course, is 1, which leads us to this. That's unsatisfactory to you. Let me show you another reason. If you FOIL this, distributive property, box method, whatever you kids are calling it these days, 1 times 1 is 1. 1 times cosine is minus cosine theta. Cosine of theta times 1 is plus cosine of theta. And then we have a positive times a negative, which is a negative cosine squared of theta. These two middle terms cancel. Still get this up here. If you need to show that work to get this correct, do it. If you don't, I don't require it. As mentioned for the 1,000th time in the last couple of days, 1 minus cosine squared of theta is sine squared of theta. We can cancel a sine from the top and bottom, which leaves us with sine of theta over cosine of theta. Tell you what, the more I do this, the more ridiculous my handwriting becomes. And I know what you're thinking, but it was already really ridiculous. That's true. Sine over cosine is the same as tangent. We've proved it. Finished. 2 more. Same directions. Tangent plus cotangent should be secant times cosecant. All right, so let's change tangent and cotangent to sine over cosine. Well, to sine and cosine, I should say. Let's get common denominators and multiply this one by sine over sine, which is the same as 1. Going to multiply this one by cosine over cosine, which is the same as 1. So I'm going to get sine squared of theta plus cosine squared of theta, that looks familiar, over sine times cosine. Sine squared plus cosine squared is 1. Yo. At this point, I start looking at the right side. Somehow 1 over sine times cosine becomes secant times cosecant. Well, what's reciprocal of sine? Cosecant. What's reciprocal of cosine? Secant. Almost the same. Can reverse their orders. That's the commutative property. And get secant of theta times cosecant of theta, which is what the right side was all along. Finished. Number 10. All right, I'm going to get common denominators on the left, and I'm going to add or subtract these little fellas together. So I'm going to multiply this by 1 plus sine of theta on the top and bottom. I'm going to multiply this by 1 minus sine of theta on the top and bottom. Hardest part about this problem for most folks is using this subtraction appropriately. People don't do a very good job of that. My denominator, I'm multiplying two conjugates. That's a 1 minus sine squared of theta. It's described earlier why that's the case. In my numerator, I'm going to have cosine of theta times 1 plus sine of theta, subtract cosine of theta times 1 minus sine of theta. I'm going to do a superpower move here. It's going to blow your minds. Actually, I won't. Yeah, I'll do it. Your mind hasn't been blown in a while. I'm going to GCF out this cosine of theta. If I do that, I'm left with 1 plus sine of theta minus 1 minus sine of theta. My denominator, as mentioned a billion times in the last couple of days, 1 minus sine squared of theta is cosine squared of theta. I'm going to try to simplify this jazz in here. So I got cosine of theta, 1 plus sine of theta, distribute the minus, minus 1 plus sine of theta. Bottom stays the same. I'm still just trying to simplify this mess here. 1 minus 1 cancels. Sine of theta plus sine of theta is going to be 2 sine of theta. Here's why that super excites me. The right side had a 2 all along. I didn't know how I was going to get a 2. It just appeared as if from nowhere. Then cosine divided by cosine cancels. Now we have 2 times sine of theta times cosine of theta. Guess what sine over cosine is? It's tangent, which is what the right side was all along. Whoops, I forgot my 2. That concludes the notes.